Hello students, today we will discuss about linear combination and linear span. First of all, linear combination. It is nothing but the sum of scalar multiples of vectors. Means here scalar, this is scalar multiplication, scalar into vector, and when you are adding these all vectors, so vector addition, scalar multiplication together is nothing but the linear combination, right? Now linear span means the set of all linear combinations, the set of all linear combinations of some vectors is nothing but the linear span. So when you are taking the span of V1 to Vp means we can take the linear combination and the set of all linear combination where S1, S2 and so on up to Sp are scalars. Now we have to prove that span of any two vectors is a subspace of V, that we need to prove. So take any V is a vector space and H we are taking as a subspace. To prove it is a subspace, we are taking the span of V1 V2. So span of V1 V2 is nothing but what? S1 V1 plus S2 V2, where we are taking S1 S2 are scalars. Now to prove H is a subspace of V means obviously what we know, H is obviously a subset of V, and we need to prove three conditions for subspace. One is 0 bar must be belongs to H. So how you can representing in a zero vector span, in terms of span means we are taking S1 V1 plus S2 V2, like 0 V1 plus 0 V2, which is the linear span of V1 V2, which is obviously belongs to H. So first condition has proved. Now take the second condition, vector addition condition. So take any two vectors from linear span, then we need to prove u plus v belongs to H. So take u belongs to linear span means u can be expressed as the vectors like this, S1 V1 plus S2 V2. Similarly, v is also a linear combination in terms of V1 and V2. Then u plus v means we are writing u plus v, then take V1 common, V2 common. So again it is in the form of like some scalar into vector plus scalar into vector, which is nothing but the linear combination of vectors v1 and v2. So obviously it is belong to span of H, span of H, that is what belongs to H. So for all uv belongs to H, u plus v belongs to H. Similarly we can prove for scalar multiplication. So take any scalar, we can write C belongs to F, or else you can belong to C is any scalar and u belongs to H. Then when you are taking C into u, what will happen? C into u, again multiply C S1 into V1, again V2. So it is also the linear combination in V1 and V2. So obviously it is belongs to H. So scalar multiplication also proved. So from 1, 2, 3 what we can say, 0 bar belongs to H, and vector addition, scalar multiplication. From that what we conclude, H is a subspace of V. In the same way, in generally we are taking p number of vectors. In the previous theorem we have taken only two vectors. In general we are taking any finite number of vectors, then span of that vectors is also a subspace of V. So similarly we can prove, there we are taking only two vectors, here we are taking p number of vectors. So similarly H is span of V1 to Vp. So span in the sense it is a linear combination of all these vectors. So S1 V1 plus S2 V2 and so on up to SP Vp, where S1 to SP are scalars. In this case we can write belongs to F, or we can write they are scalars. Now to prove H is a subspace of V, obviously we know that H is a non-empty subset of V, and it is enough to prove 0 bar belongs to H. So 0 bar, how you can representing as a linear span? It is a combination of linear combination of V1 to Vp. So 0 V1 plus 0 V2 and so on up to 0 Vp is nothing but 0 bar. So it is belongs to H. So first condition has proved. Similarly, vector addition condition. Take U in the linear combination of V1 to Vp. Similarly, V as a linear combination of V1 and Vp, where S1 to Sp are scalars, here T1 to Tp are scalars. Now take u plus v, then write u plus v, then take v1 common, v2 common, like that up to vp. So obviously what it is? It is a linear combination of vectors v1, v2 and so on up to vp. So it is belongs to span. So it is belongs to H, where these numbers are scalars. So vector addition has proved. Similarly scalar multiplication, C into vector, then multiply, then also you are getting the linear combinations of vector v1 to vp. So it is obviously belongs to H. So scalar multiplication has proved. From all these three conditions what we can say, H it is nothing but span of v1, v2 and so on up to vp, which is also a subspace of V. Okay, now let us see one another problem. Here H is given as some vector like A minus 3B, B minus A, B. Here we have 4 vectors, four entries where AB are arbitrary scalars, that is AB belongs to R, then show that H is a subspace of R power 4. So here in one vector, this is one vector which contains how many entries? 1, 2, 3, 4. So it is belongs to R4. So R4 is a vector space here and H is given like this form, where this A and B are belongs to R. So, to prove it is a subspace of V, in the previous theorem, we proved by using three conditions, that is 0 bar belongs to H and vector addition and scalar multiplication. But in the previous theorem, we had proved that span of V1, V2 and so on up to Vp is also a subspace of V. So, to prove H is a subspace of V, it is enough to prove is there any, it is in the form of linear combinations of vectors or not. Let us check this one. So, take this vector and A minus 3B here write in a proper manner like A term then B term. Here B term is first, so we can write as minus A plus B. Here only A term is there, B term is not given, so A plus 0 into B. Similarly here 0A plus B. Now we are getting the terms in terms of A and B. Now take A as common. A as common, what will happen? In the first element, A coefficient is 1. In the second element, minus 1. Third element, 1. Fourth element, A coefficient is 0. Similarly, take B as common, then minus 3, 1, 0, 1. What it means? It is nothing but some scalar into vector plus another scalar into vector. So, suppose we are taking this as V1, this as V2, then what we can write here? A V1 plus B V2, where V1 equal to this and V2 equal to this. It is nothing but what, girls? Linear combination of vectors V1 and V2. Now, so we can write it as what? Span of V1, V2. So, H can be expressed as linear combination of vectors V1 and V2. So, obviously in the previous theorem what we proved? It is a subspace. So, span of some vectors, finite vectors is a subspace of V. Here it is given 2 vectors. So, H is a subspace of R4. Similarly, we can do another problem. So, like this, one vector is given. To prove it is a subspace of R4 or any Rn, then just it is enough to prove that it is the span of that vectors or not. So, to check that one, first of all, how you can identify the vector space means a vector which contains how many entries? It is nothing but what? It is a subspace of R4. Here, subset of R4. Here, R4 is a vector space obviously, and W contains 4 elements in one vector. So, it is obviously a subset of R4. So, it is enough to prove what? It is the span of 2 vectors. So, let us check. Now, take here S term, T term is there. Here S term is there, but T term is not there. So, we can write it as what? 0 plus 0T plus 0T we can write. Here S is not there. So, 0S plus T we can write. Okay. Then S common, then coefficients of S 2, 2, 2, 0. Next T common 4, 0, 3, 5. So, what we can write? S into some vector plus T into another vector. So, it is the linear combination of V1, V2. It is nothing but what? Span of V1, V2. So, obviously what we can say? It is the subspace of R4. So, see here H is the subspace of V. So, here given W, that's why W is a subspace of R4. Similarly, we can do another problem. W is given, then it is a subspace of what? What is the vector space? Can you guess? Here we have 3 entries. So, obviously it is the vector space is what here? R3. So, R3 is a vector space and W we are taken where B and C belongs to R. Here 2 scalars are given in the sense how many vectors will get? Obviously 2, because linear combination means how many vectors are there, that much of scalars must be there. So, here 2 scalars are given in the sense we should get 2 vectors. Let us see. So, it is B.Sc combination of B and C. Similarly, directly also we can write here. Otherwise, we can write as minus B plus 0 into C. Here 0B plus 2C. Then, by taking B common, we are getting one vector. C common, we are getting another vector. Similarly, we can write here u and v, because in the question it is given that find the vectors u and v it is asking. So instead of v1 v2 we can write u and v. So same type of question, but the representation is different. So here it is asking that BC are arbitrary, then find the vectors u and v it is asking. So we are finding the vectors and take it as u and v. So it is a linear combination of u and v in the sense span of u and v. So we know that span is always a subspace of vector space. So W is a subspace of R3. The same way H is given. Here how many elements are there? T is a real number. Only one T is there. So only one vector we should get. Okay. So see here 3 entries. So R3 is a vector space, and from H what we have to take common? T as common, then 3 0 minus 7. So T into some vector we can choose any one, U, V, V1, U1, anything it is fine. So T into V1 where V1 is equal to the given vector. So it is a linear combination of single vector. What we have learned? It is any finite number of vectors, then span of that vectors is a subspace. Here one vector is this, no issue. So H is the subspace of R3. Now see another problem which has given in always in every year this question will be come. So here H is given as ST0. H is a subspace of R3. First of all, what we need to check is R3 vector space is given in the sense it should contain 3 entries. Okay, it has 3 entries. Now what we have to check is how many real numbers are given here. ST are real numbers. So how many vectors will come? 2 vectors will come. So write this ST0 in the linear combination of S and T. Here only S is given, right? So S1 into S plus T is not given. So 0 plus 0 into T. In the same way here only T is given, so 0 into S plus 1 into T. Now here 0 is given means 0 into S plus 0 into T. So when you are writing like this, then it will be easy to find the vectors. So take S common, then the entries, then T common, then the coefficients. Now it is a linear combination of S and T where V1 is first vector, V2 is second vector. Okay, so it is the subspace of R3. Similarly, we can have another problem. Here only T, single T is given. To prove it is a subspace, we should get one vector. That is what, when you are taking T common, then the coefficients should be right. Then this is the vector. So it is a linear combination of one vector. So it is also a subspace of R3. Okay. So in the next video, we'll discuss more problems about subspaces and linear combination. Thanks for watching.